live. Okay, so today is 12/16, and we're learning about parametric equations. And parametric equations give us position, some x, y value, position, x, y, right, on a graph, and time. And we're going to let time just be in terms of seconds. It's the easiest application. So when we're moving along a graph, we're just going to say from t0 to t1, 1 second expired. That's not always true, but for what we need, time is just going to be per second, okay? So these are parametric equations. This x sub t is an x value, okay? So when you see x sub t, it is a horizontal movement. When you see a y, it's a vertical movement, but over time. So you need two equations to do it because it's going to move in two directions over time, okay? So we want to do this from -1 to 2. So time is going to go from -1 second, so we're going to go back in time, find out where it was, and we're going to go from -1 to 0 to 1 to 2 seconds. So the easiest way is a table of values. So I'm just going to do a t-table, but not a normal t-table. A t-table with time, an x value, and a y value, okay? So think about, we have a bug on the graph. The bug's going to move along the graph. So first of all, if at -1 seconds, at t equals -1, we're just going to plug in, t equal -1 into both x and y, and we'll find out the position at where it's at -1. So if I plug in -1 for t, -1 minus 3 is a -4, so its x value would be -4. 2 times -1 is -2 plus 4 is 2. Okay, so I just plugged in -1 as a value for time into t, and I got an x value. I plugged in -1 for t into the t to get a y value. So I know that where it was, 1, 2, 3, 4, 1, 2, it started t -1 right there. And we go t sub -1 because it tells us where was the particle or where was the bug a second ago, right there. So then we plug in 0, okay? So where was it at 0 seconds? So we plug it in. Plug 0 in for t. 0 minus 3 is -3. And 2 times 0 is 0 plus 4 is 4. So at 0 seconds, the particle, or the bug, was at -3, 4. T sub 0. So it's moving in this direction. It started here, it's moving in this direction. So now we plug in 1 second. So 1 second, again, we plug in the 1 for the t. 1 minus 3 is a -2. Plug in the 1 in for here. 2 times 1 is 2, plus 4 is 6. So the particle, or the bug's at -2, 6. So 1, 2, 3, 4, 5, 6. That's at t sub 1. And then finally, at 2 seconds, we can go t is 2. If I plug in 2 for time, 2 minus 3 is a -1. Plug in the 2 in here. 2 times 2 is 4, plus 4 is 8. So my particle is at 2, is at -1, 8, which is here, okay? T2. So it's moving along this path. So not only do we get a path, but we get a time. So we know that at -1 seconds, or back in time, this is where it was. At 0 seconds, it's at this position. At 1 second, it's this position, and at 2 seconds. And if it kept going, it would just keep moving along this way. But I put arrows on it because it shows the path. The arrows are important because we know which direction it's going, correct? Okay, pretty easy? Okay, now, let's take a look at, you got your calculator? Okay, so if we take a look at this on our calculator, and we go to our mode, okay, go to your mode, and instead of polar, we're going to go to pair. And pair stands for parametric, right? So enter. So I'm parametric, and when I go to y equals, I get a x1 of t and a y1 of t. So I get a x of t and a y of t, right? And what I want to do is put these equations in. This is my bug path. So I'm going to put my t. So if you want, when you put x, when you push this x value, it's going to hit t because you've changed the mode. Go right here, hit that button, it'll hit t because you've changed the mode to parametric. So I'm going to go t, subtract 3, and I'm going to go 2t plus 4. How am I doing?
Good.
Okay, now the window is kind of important. The window is very important. So if I go to the window, my window, I'm given time. So we wanted to go on time-wise from -1 to 2 seconds, correct? The time I have is 0 to 6. I don't want that. So let's change this to a -1 to 2, okay? -1 to 2. So I'm going to go time. I'm going to go -1 to 2, okay? Seconds, we're going by ones, right? 1 second, 2 seconds. My scales are by 1 second, 2 second. Now, if I take a look at my graph, I should probably make my x min and x max fit. So -5 would actually work, wouldn't it? I didn't need to quite go to 5, but 5 can be there if I wanted to. It doesn't hurt. I don't quite need to go down to -3, but it's okay. But I might just change that to 0. What the heck, right? To my y max. Oh, my y max is probably as high as maybe 8. What do you think? Y max is
9. Let's go 9.
You want to go 9? Okay, I'll go 9. Okay, 9. Okay, so then if I go graph, there it is. Okay. Okay, here's what's different. Normally lines go forever, don't they? But this one only went from here to here. Why? Why did it only go from here to here? Come on, think. Why did it only go from here to here?
Domain.
Right. And our domain is time in this case. We said from -1 to 2. Now, if you want this line to be longer, you can let the darn bug go longer. So you'd have to change the window and change the time, okay? Steps are 1, max is 2, steps are 1, 0. Oh, 0 to 5. We got -5. Oh. Right, you're going backwards, right? Scales by 1. You want to go from, say, 0 to 9. Then finish work. Oh, well, come on, everybody. There it is. Okay, now. Watch the second thing, okay? Go to, everybody watching, go to trace. Go to trace. And when I hit the trace button, it gives me 3 things. This is kind of cool. It gave me a time. So at -1 seconds, it's at -4.2. Right? And if I then move the cursor to the right, at 2 seconds, what's it say? At 2 seconds, so at 0, when time is 0, it's at position -3.4, right? And if I move it along again, boom, at 1 second, the position's at -2.6, and then at 2 seconds, the bug, or the particle's at -1.8. Okay, now if we wanted it to go and keep going, what would I change if I wanted the bug to keep crawling along? What would I change?
Y max.
I could, Y max definitely, but it stopped. Let me go back. It stopped right there. So it stopped here. Think about in time. You know, boom, 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 it stopped. Time.
So we would just add more time.
Add more time, Zoe. Yes. So if I go back to my window, and Zoe, how long do you want the bug to run?
100.
No. 19 seconds.
19 seconds. If we do 19 seconds, we'd have to change our Y. Right, Zoe? You said 19 seconds, so I'd have to change my Y window. I got to make it go a lot taller than that, right? And my Y max, I might make, maybe 25. I don't know. Maybe even that's not long enough. That's not even long enough, right? For 19 seconds, it's still going, so I might go my Y window, Y max. I might go, let's make that maybe 35. My X max, maybe.
Still not.
Graph, right? Still not long enough, so we can keep playing around with it until we've got the thing running far enough. I have to change my x max probably, right? X max probably 20. And you
Oh, I
keep.
got it.
Did you get it?
Yeah.
So it stops.
Yeah.
What do I want to make my x max to?
50.
Okay, and my y max?
No. X max just needs to be 20, and then Y max needs to be 50.
Okay, let's see it. There it stops. Good. So at 19 seconds, it stops here. And if I want that position, I can do one of two things. I can plug 19 in for t, or I could use my trace button and go to 19 if I want to know where it is. So, I mean, think about this as a real-life problem. You're a scientist, you're a physicist, you got a particle, and you want to know where it's at 19 seconds. You could either plug the 19 into our formula, or we can go to our trace and go 19, enter, and it tells us our particle's at 19 seconds. It's at a position of 1642. Okay, thumbs up? Kind of cool, huh? Okay, now, number 2. Let's look at example 2. So example 2. So an object travels along a straight path from -5, 1, 2, 3, 4, 5, 3. Okay, so it's going to start here. Okay, call that point A. And then it's going to go to 3, -1. Okay. So our bug, this is more like land, and see how he's going to cover a lot of distance in a quick time. So this bug's running. Does that make sense? If that's 1 second, this bug's going a lot faster. It's like a Landon bug instead of a Morgan bug. Okay. Now, if I want to be able to put this into my calculator as far as time and parametric, I need 2 parametric equations. So I need a x of t and a y of t. Okay. So let's see what happens. So we started. What's the x value here? So this x value is at -5, 3, right? So it started. The x value started at -5, right? And then it moved. Here's your velocity. Okay, Sky, here's your velocity. It moved from here to here. In how many squares? It moved from here to here in 1, 2, 3, 4, 5, 6, 7, 8 squares. You see that? So it went forward 8 squares. It went forward 8 squares. So we're going to go plus 8t because it moved 8 squares in 1 second. Does that make sense?
Where did the negative come from?
Where it started. It's x value. Now, what about the y? We're going to do the same thing with y. Where does it start with y?
3.
And then it moved down. How much moved it down? It moved down 1, 2, 3, 4, 5, 4,
No,
right?
4.
Down 4. So the y value went down 4 t. Okay, now if we wanted to graph this, we can do the same thing. Okay, so I'm just going to go, and I'm going to have to change my window. I change everything, but if I go clear. If I want to put this in my calculator, I can. I'll go -5 plus 8t. Oh, hold on. Here we go. -5 plus 8t. And the other one is going to be 3 subtract 4t. I'm going to change my window. Okay.
We can't really see your count. Oh, there we go.
There you go. So x and y, there it is. I put them both in. Thanks, Zoe. I'm going to change my window so it fits my problem. Okay, go to my window. And so we only ran 1 second, right? So we can go from 0 to 1. If we want to do 0 to 1 second, okay, because we only ran 1 second. We can go 2 seconds if you want it to keep running. It's up to you. Do you want it to keep running for 2 seconds or just 1 second? Just 1 second, so 0 to 1. Steps by 1. Probably -5. I'll go probably -6, so I see a little bit more of it. For the x max, or x min, x max is only 3, so I'll put it at 4. You with me on that? Scales by 1. My y minimum is -1, so I'll probably go -2. Let's see, my y max is 3, but I'll probably go 4. And graph it. Okay, there it is. It's exactly what we have on our graph, right? And if I wanted to go to trace, I can. Starts there. 1 second later, it's moved to there, okay? So, all right. Now, example 3. This is where, if you take calculus, this is where parametric equations come in really handy. A lot of times in calculus, it would be really nice to know what this looks like, but you can't graph this. You cannot graph this, and you're going to have a heck of a time changing this into point.
Will it say air?
You will say error, because you won't be able to solve for y, okay? But what we're going to do is this. If we change it into parametric, we'll know what this equation looks like, okay? So here's how you change it into parametric. Okay, now, if you let y equal t, so if I want to parameterize it, or change it to parametric, I'll go x of t and y of t. Start there. When you want parametric equations, just start right there. Parametric equations takes both an x of t and a y of t, okay? Now, I said let y equal t. So instead of writing y's, let's write t, okay? So we're going to rewrite this as a t cubed minus a 2t, and I said y equals t, didn't I? I said let y equal t.
Yes.
Now, if I were to take my calculator and graph this, then if I was sitting in a calculus problem, if I really needed to know what the graph looked like, I could put it in parametric. It's kind of slick because this graph is really difficult to see, this one. But if I go to t cubed, subtract 2t, and, oh, hold on, sometimes I hate these new calculus clear. Let's go t cubed over arrow minus 2t, and if I just go t. So before I hit enter, here's what I have. Okay, so if I wanted to graph x equals y cubed minus 2y, if I want to graph this, you can't. You cannot graph this. But if you change it into parametric, you let y equal t, and you substitute t in for y, and you'd be able to graph this and see what the curve looks like, okay? So if I go to graph, I don't have much of a graph at all, okay?
Oh, it's cute.
Now, I want to see more of it. So how can I see more of this graph? Think about it. It's a bug.
Time.
Yeah, time. Think of this. I didn't get much. That's all the further I saw it. I want to see more. Let's see more time. So let's go back in time and forward in time, because back in time might give me one picture. Don't know where it went, where it came from. So if I go to my time, so I go to my window, okay? So I go to my window, and let's make my time, let's go -3 to, say, 3, and I might see more of it, okay? So I change my time so I can see where it came from and where it's going. So now if I graph it, okay?
Whoa.
Now, looks kind of chunky, doesn't it? Right? But we know if it's cubed, it's going to be curvy, okay? So, I don't know if you guys have ever seen a strobe light.
Yep.
If you ever watch a strobe light, here's what a strobe light does. Flash, 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 right? So if you're like playing cops and robbers, right? Wow. And all of a sudden, boom, boom, and then who knows what land could have done in between, right? Because it's just flash, flash. So this is like 1 second, 2 seconds, 3 seconds. Something might be happening here. So I'm going to change the time. But when I change my window, instead of going like, listen, instead of going flash, 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 what if I go, keep the flash going? Does that make sense?
Then we'll see parts of it.
So instead of every flash every 1 second, what if we flashed every 1/10 of a second?
Or what if you don't even flash it?
Right.
You turn it on.
Yeah.
So but we can't do that with parametric. We have to have a time. So I'm going to go, I want to see it every 1/10 of a second. So if I change it 0.1 seconds, it'll take it longer to graph, but I'll see where it's at. So if I graph it,
This is beautiful.
I get a much better picture where it's at, right? Now, really easy question. Is this a function?
No.
No, so you cannot graph this normally. But another parametric you can. If you're doing a calculus problem, you get some really nice information about this curve because you can now see it, right? Pretty cool. Okay? All right. Turn the page. All right, now, we can go the other way. So given, if I have x of t and y of t, so this time what I want to do is put it in an xy, because I want to see xy graph, what does it look like, because there's some things in calculus I could do with an xy versus parametric. So here's what I'm going to do. Okay, I'm going to set them up. I'm going to go, okay, x is equal to t squared plus 1, and y is equal to 2 plus t, all right? Now, if I want Cartesian, I want x and y's only. X and y's only. Okay, no t's. X and y's only. So I got to get rid of t's. No t's. Okay. So I'm going to get rid of t's by substituting. So if I take my second equation, which is easiest to solve for, this one's a little bit harder to solve for t. Okay, if you had to pick one to solve for t, this is the easier one to solve for t. Subtract 2, right? This one you have to subtract 1 and square root, right? So let's solve for t. So t is equal to y minus 2, because I just brought the 2 over, okay? And I'm going to take the y minus 2 here, and I'm going to substitute it in for t squared. So I'm going to rewrite this equation as x is equal to, parentheses, y minus 2 squared plus 1. Okay, all I did is make a substitution. I had to solve for t. So I solved for t. Made a substitution, okay? And now I'll simplify it. X is equal to y squared minus 4y plus 4 plus 1. I foiled it in my head. I'm hoping you guys know how to foil it in your head. You do know how to foil this in your head, don't you? Can you foil that in your head?
Yes.
Okay, that's all I did. I'll make that a 5, okay? So if x equals a y squared minus a 4y plus 5, okay? Now, these two are the exact same curve. One's in parametric and the other's in regular xy or Cartesian, okay? Okay, last but not least, okay? Now, we've got x equals 4 cosine of t and y equals 3 sine of t. And now this one, I want to get rid of the t's, and dang it, it's inside cosine and sine. So how do I do this? Well, it takes a little trick, okay? And here's my little trick. Let's write this up. We know this identity, because I'm going to use this identity. I know that sine squared plus cosine squared is equal to what? Sine squared plus cosine squared is equal to what? Say it. I heard it. What is it? 1. You guys agree with Patricia? We learned that last chapter, okay? So what I want to do is make these into sine squareds and cosine squareds so I can substitute it. Okay, so first of all, let me divide by the 4. So I've got x over 4 equals cosine t, and y over 3 equals sine of t, okay? Now my goal is to go sine squared plus cosine squared, okay? That's my goal. Because sine squared plus cosine squared originally came from x squared plus y squared equals 1. Wasn't that my identity I originally got it from?
Yeah.
So, let me square both sides. I'm going to square both sides. And I'm squaring both sides because I want a cosine squared. Let me square both sides because I want a sine squared, right? So I'm left with an x squared over 16 equals cosine squared t. And I get a y squared over 9 equals a sine squared over t. Now, here's what I'm going to do. So, instead of writing cosine squared, I'm going to write x squared over 16 right there. And instead of writing a sine squared of t, I'm going to write a y squared over 9. So when I substitute, I'll have a y squared over 9, because that's what t squared is equal to, plus, instead of writing a cosine squared, what does cosine squared equal? X squared over 10 over 16, and it equals 1. So what I did is I went from t's, x's, t's, y's, t's, into just x's and y's only. So I changed it from parametric into regular Cartesian or XY. Now, I like this better originally, because this you can't graph. This is an ellipse. You don't know that yet, but this is an ellipse, okay? But you don't know that. You don't even know what this looks like. But if I went back, and why do we do parametric? Well, if I do, wrong calculator. Because if I do parametric, it'll work. In fact, let me go ahead and put it in clear. And if I go into my original 4 cosine of t and my 3 sine of t, right? Check my window. Okay, and this time I'm going to go 0 to 2 pi. There's a reason I'm going to 0 to pi, because I'm going to go around a circle. And let's graph it. And it is an ellipse. I want to see a little bit more of that. Window. Change my y min to maybe -4. There we go, graph that. And there it is. Okay, now, why is this helpful? This is not a function. You guys agree? That's not a function. You cannot graph it from here. You can't. But once you have it in parametric, it's kind of a cool graph. You can see what it looks like. Okay? Isn't that neat? I think it's neat. Of course, yes, I am a math nerd. I wear it proudly. Okay, so that's what I got to do.